Yes, perfect. Thanks. So yeah, as I was saying, today we have Abel Laval from Université Libre de Bruxelles. And yeah, the floor is yours, Abel. So please take it away.
Well, thanks first for the invitation and the introduction. So today I will talk about a generalization of the KLPT algorithm, which is like cleverly named KLPT². And as you can see, there is like capitals in the name, but that's absolutely normal. And if I have some time at the end of the meeting, I will just explain this. Oops, yes. So once for all, I will just fix some constants and some notations. For the whole talk, we will have P, which is a prime 3 mod 4. This is not mandatory, like in theory, but it will help us a lot to explain a simpler case. We'll have like a small prime L, which is basically like 2 or 3. E0 will be the supersingular elliptic curve with J invariant 1728 over fp². O0 will be the maximal order of the quaternion algebra isomorphic to the endomorphism ring of this curve. BP infinity, the underlying quaternion algebra. And A0 will be the product, so it's an abelian variety already. It's a product E0 times E0. And lambda 0 we'll see is some function, some map called a polarization associated to A0. So here I assumed some basic knowledge about quaternions and quaternion algebra. Yes, that's like the basic requirements for this talk. And this talk, I won't write it, but every single elliptic curve will be supersingular. Okay, so at the core of isogeny-based cryptography, we have on the left the isogeny path problem. So here's like some variant of the path problem, but it's not really important here, which is just given two elliptic curves E1 and E2, phi and isogeny phi of power of a prime, the degrees of power of a prime that connect the two curves. And actually, there is an analog of this problem in the quaternion world, which is instead of having elliptic curves, you have maximal orders in a quaternion algebra, and you're asked to find an ideal I of prescribed norm such that the left order of this ideal is O1 and the right order is O2. So in some sense, I is connecting O1 and O2. And actually, so these two worlds are just connected through what we call the Deuring correspondence. So if you want some introduction to this, we recommend another talk of the Isogeny Club, one of the first ones, by Antonin Leroux, which is really clear in my opinion. And so we have this Deuring correspondence. So what I must say that you cannot compute it explicitly, of course, like just trivially, you need some information to do so. And the information you need is the endomorphism ring of the elliptic curves E1 and E2. Okay, so from this, we have a clear strategy, more or less, for solving the isogeny path problem. So on the left, you have E1 and E2, which is the instance of the problem, and you want to find phi, which is a solution of the problem. And to do so, you will translate first your problem into the quaternion world. You will solve it in this world using the KLPT algorithm, and then you will translate back into the world of elliptic curves. And so in theory, at least, it gives you like a solution to this isogeny path problem. But of course, the important part here is that this does not break isogeny-based cryptography, because to do these translations, the correspondence translations, you need to know the endomorphism rings of E1 and E2. And Veselowski showed that actually knowing these endomorphism rings is equivalent with like a learning phi. So yeah, it does not break everything just like this. And so the goal of the talk here would be to build an analog of this picture in dimension 2. And so we would replace pretty much everything. So the elliptic curves will be replaced by abelian surfaces. The maximal orders O1 and O2 will be replaced by some matrices. I will define how we find these matrices. The Dori correspondence is replaced by something else called the Ibukiyama, Katsura, and Oort correspondence, which is just an analog in higher dimensions. And of course, the solver, which is KLPT, is replaced by KLPT². Okay, so the organization of this talk would be like in 4 steps. First, I will like try to put an emphasis on explaining the tools we're dealing with, because if KLPT² as an algorithm is just solving some equation, even if you don't know what it means, if we really want to understand where it comes from, it's really important to understand the tools we're dealing with. And so the first part would be understanding these tools. Then I will describe the correspondence, the generalization of the ring, then KLPT, and then I will give some applications of this. And on the right, you can find like the correspondence between these chapters and their sections in the imprint. But since the imprint is not available yet, well, I don't really know what you can do with this. So the first part is we have this awful name, which is principally polarized superspecial abelian surface. And the question is, okay, what is this? How is this the generalization of simple empty curves? Well, to understand this, we have to split this name in 3 parts. So first we have abelian surfaces, then we have being superspecial, and then we have being principally polarized. And so we'll tackle these 3 parts separately. First, if you look at some algebraic geometry book or Wikipedia even, you will read that an abelian variety is some algebraic group with some projective space embedding. And that's like really abstract objects. So it's not really good for intuition, but actually we can classify these varieties by the dimension. So in generic dimension, it's quite hard, but in dimension like 1 or 2, it's not so bad. So in dimension 1, every abelian variety is just an elliptic curve, E, so we use to this case. And in dimension 2, we have two possibilities. Either the variety is isomorphic, no, it's not isomorphic, it's equal to a product of 2 elliptic curves, or it is the Jacobian of an hyperelliptic curve. And yeah, if you want, again, an introduction to Jacobians and abelian surfaces, another Isogeny Club talk I would recommend is those of Sabrina. And so an abelian surface is just a variety that has dimension 2. So that's first part of the definition. Something that will be really important for what follows is the notion of dual. So when we have a variety, we automatically have attached to it some dual variety that is like canonically defined. So if I have A, I have some A dual, which is a variety as well. So if I have B, I have a dual of B. And if I have an isogeny between A and B, it defines automatically an isogeny, a dual isogeny between B dual and A dual. So how these like varieties, dual varieties are defined is not really important for us at the moment. Yeah, you can see them as like set groups of divisors because in fact they're just the Picard group of the variety. And again, if you want like a basic introductions, there is like Ben Smith who talked about this quite clearly at Isogeny Days. And one remark that is important at this point is that this phi hat you can see, you might think it's the dual isogeny we're used to in dimension 1, but actually no, it's a different thing. And yeah, we'll see that the dual isogeny, what we call the dual isogeny, is something different. And indeed here, it doesn't go from B to A, but from B dual to A dual. Okay, now we can talk about what superspecial mean. So if you take an abelian surface, so it's any abelian surface, so a Jacobian or product of elliptic curves, it can be isogenous to a product of elliptic curve, in which case we say it's supersingular, or it can be isomorphic to such products, in which case we say it's superspecial. So basically, in dimension 1, we only have one notion, which is supersingular, because the two notions are equivalent. But in dimension 2, they cease to be equivalent, and we have like to make this distinction. And so, so we have two notions, and we want to see what notion is the best if we want to do cryptography. So we have to look at the isogeny graphs. And in the first case, in the supersingular isogeny graph, well, it's in dimension, it's an object of dimension 2, and in particular, it's infinite. So we have infinitely many vertices, which is not really good because for cryptography, we would like a finite graph. And so we would like to use a superspecial graph instead. But the superspecial graph is not good either, because here it's the converse problem. We have only one vertex. So on the left, we have too many vertices, and on the right, we have like too few. And the reason we have only one vertex here is explained by a theorem by Deligne, which just says that any two product of elliptic curves is isomorphic. So if you have two superspecial varieties A and B, by definition, they're isomorphic to some product of elliptic curves, and these products like are isomorphic. So we only have one vertex. So this graph is not good either. So to solve this problem, what we want here would be a finite graph, but with like exponential size. And to solve this problem, we will take the superspecial Jacobians or like surfaces, but with extra information to remove some isomorphisms in some sense and have more isomorphism classes. So this leads us to the definition of a polarization. Like the actual definition of a polarization is quite ugly, so something based like on algebraic geometry. But what you have to remember, the only basic intuition you need is that it's a map from a variety with dual. So the definition involves ample divisors, and even there, which is like a definition you will see, like not everywhere, but like in various places, I think it's not exactly correct because there is some abuse notation here, because instead of D, an ample divisor, it should be some ample line bundle. But yeah, so that's not really important in the end. What is important is that a polarization is an isogeny first, which is something we know how to manipulate. And it's an isogeny between a variety and its dual. And so some important properties to know that not all isogenies between a variety and its dual are polarizations. So they're still like they're a bit specific as isogenies. And if a polarization has degree 1, it's called principal. So in this case, the polarization is an isomorphism, and you can invert it in particular. And yeah, so principal polarization is just an isomorphism between a variety and its dual. And we will write p-pol of A for the set of principal polarization on A. With this new object, we can define polarized isogenies. So you take two polarized varieties, A and B, with the polarizations. And here in the diagram, you really have to see like the left side is really like one object, A, its dual, and the isogeny between the two is really like one object, it's one variety, a polarized variety. And on the right, you have a second object. And so if you compute an isogeny between A and B, it will automatically induces a dual isogeny between B dual and A dual. And so an isogeny between the polarized varieties is just an isogeny between the underlying varieties, such that this diagram commutes. So here you can see we just had like extra coefficient n appearing on the left. N in this case is the degree, the reduced degree of phi, and is required so that the diagram commutes. And so one important way to see polarized isogenies is this equality I show you here. And what's important is that, in some sense, the isogeny is like a conjugation of lambda b. So you go from lambda a to lambda b by conjugating by phi. Okay, so if we sums up everything we have so far, so abelian surfaces are either like Jacobians or product of elliptic curves. Being superspecial means that the variety is isomorphic to a product of two elliptic curves. So in this case, I wrote E0 times E0 because this is isomorphic to any product. So this is valid. And this isomorphism is as non-polarized varieties. If you add polarization, of course, it's not true anymore. And principally polarized mean that we have an isomorphism between the variety and its dual. And if we look at the isogeny graph here, it has like all the properties we want, like most of the properties at least, because it's finite first, and it contains big O of p cubed vertices, which is like exponential in the security parameter. And if you look at all the vertices, most of them are Jacobians, and like some of them, but they're like really sparse, are product of elliptic curves. So the generic case are Jacobians. Okay, so we solve our problem. We have a nice graph to work with. So a small like sanity check, just to be sure we understand what we're doing here. If you took a E0 as an elliptic curve, so it's still like the supersingular classic one, it actually comes with a polarization, which is canonical, which sends a point P to this divisor, P minus the point at infinity. And it's the only polarization on E0. And that's why we don't talk about polarization with elliptic curves. It's that just because that you only have one up to equivalence, actually, but you only have one. So it's not really interesting. Now, if you look at A0 with a product polarization lambda 0, it is superspecial because, of course, it's isomorphic to a product because it's equal to a product of elliptic curves. And it comes from a natural polarization lambda 0, which is a product polarization of E0. So just the polarization above, but yeah, twice, basically. But this polarization is not unique. You have like a lot more of them on A0. And a third example is like something more generic, I guess. Now, if A is some Jacobian, so it's defined with some equation. It is superspecial, not every time, but like for special P's. And what is important here is that just writing this equation, y squared equals x to the 6 plus 1, implicitly induce a polarization. So actually, every time you manipulate something like concrete with some equations or anything, there is a polarization behind. The only way basically to work with a non-polarized variety is just to see it as an algebraic group, which is like super abstract. Okay, so now we define the main tool of this. So now the question is, we want to interpret these abelian surfaces, which are geometric objects, as matrices with quaternion coefficients, which is exactly what the Toyering correspondence does in dimension 1. And here in dimension 2, it will be the Ibuki-Yama, Katsura, and Orff correspondence. So this is done in 2 steps. First, we take the input abelian surface, and we will transfer it into polarization. And then the polarization will be transferred to become like a matrix. Okay, so first step from surface to polarizations, you have some A lambda A, and you want to encode it as polarization lambda on A0. And it's just done by computing a pullback of this polarization. So to do this, you find some isomorphism between A0 and A, and you compute lambda such that the diagram commutes. So a few questions here already. First, phi always exists because A0 and A are superspecial, so there is always an isomorphism between the two. Second, computing this isomorphism is not easy in general. actually there is a paper, a really recent paper by Gaudry, Soumier, and Spanlower. It's on the print server since I think a few weeks ago, that solved this problem. So computes such a file when A, I think, is a product of elliptic curves. Well, at the beginning, it was even more with more constraint than this. But thanks to a remark by Veselowski, it was possible to generalize a bit. But it's only at the moment for product of elliptic curves. I don't think we have any algorithm to compute such an isomorphism for if A is just Jacobian, for instance. But anyway, so we can pull back, so transfer the information of this polarization into a new polarization lambda. And now the second part is encoding this new polarization as a matrix. That's where an analog of the ring correspondence really kicks in. And so that's why I would call it Deuring for the people. So given a polarization, you want to interpret it as a matrix. And to do that, we just post-compose it with some canonical inverse polarization. So you have polarization lambda, you just compute it, and you apply lambda 0 inverse, and it gives you an endomorphism of A0. And indeed, you can compute the inverse of your polarization because it's principal, so it's an isomorphism, so you can invert it. And so now you have some G, which is an endomorphism of A0, and under the Durbin correspondence, you can interpret this as a matrix, a 2-2 matrix with quaternion coefficients. Okay, so now if we look at the image of this map mu, so it will give us matrices, but you cannot reach any matrices. And actually, the matrices you reach with this method have a really specific form, and that's exactly what Ibukiyama, Katsura, and Oort showed, that we have this set mat A0 with this form, where S and T here are integers, positive integers, and or bar are quaternions. And here the or bar is just the conjugate, regular conjugate in the world of quaternions. And they have these matrices have determinant 1. And these will be the inputs of KLPT2. That's what will encode our varieties, and that will be the input of KLPT2. Okay, if we look at, that's not exhaustive, but if we look at the correspondence so far, so in the graph, in the geometric world, we have polarized varieties, and in the quaternion world, we will have matrices of the type I just described. The edges will be isogenies on the left, and connecting matrices, which can be in this case any matrix U in M2O0. That's encoded an endomorphism actually. The adjoint map will be this phi tilde is actually what we call the dual map in dimension 1. So it's not exactly the dual map because dual map appears in the formula, but that's a more complex formulation for the dual map, what we call the adjoint. And the equivalent of this in the quaternion world consists of the conjugate transpose of U. So here U was A, B, C, D, and so you take the conjugate transform. We have some property. The first one we saw it already. So if phi is a polarized isogeny, so it preserves the polarizations, we have this property that phi hat lambda 2 phi equals an integer times lambda 1. And the equivalent in the quaternion world will be, well, just translating and replacing these by matrices and taking the conjugate transpose for the matrix U. And we have a notion of norms. Well, norms are a bit problematic in this paper because we have 5 different notions of norms, I think. So even for isogenies, you have the reduced norm, which is used most of the time. And then you have the norm, which is the square of the reduced norm. And in the quaternion world, it's not so clear because the the ring in which you take U is not commutative, but there is a way to still define the norm, which is like quite intuitive. Like, for instance, if U is Hermitian, so if it's equal to its conjugate transpose, sorry, then the norm is like super simple to define. Okay, so if we want to state our problem really clearly, so the isogeny path problem asks us to find some isogeny phi such that this diagram commutes. And the norm of phi, the reduced norm of phi, must be like power of a prime. And the theorem, like, it's not proved like this in Ibukiyama, Katsura, and Oort, but the idea is that it reduces to find some endomorphism psi, such that, so we start with the inputs on the left and on the right. Then we will transfer these inputs, like encode these inputs as polarizations on A0, then like this. So now we have two polarization, n lambda 1 dash and lambda 2 dash. Then this polarization, we will encode them as endomorphisms of A0. So by applying this mu map. And now what we want is find psi, which is an endomorphism, such that the whole thing commutes. And so here I write what it means in the world of abelian surfaces and the equivalent in the world of quaternions. And then, of course, yeah, we can output the solution in the end would be like the composition of these two isogenies on the top, phi 1, psi, and phi 2, and we have to invert phi 1. So yeah, which is possible because phi 1 is an isomorphism. Okay, now we can finally start with the theorem itself, with KLPT itself. So the theorem is given two inputs, G1, G2, that are like matrices, like in maths O0, and there is a exponent O in this, which is not exactly what I wanted, but whatever. There is an algorithm, like a polynomial time algorithm, that computes some connecting matrix gamma, such that we have this relation gamma star G2 gamma equals n times G1 for n smooth, and more precisely here actually, n will be a power of L. And this equality exactly means that gamma encodes polarized isogenies between the varieties encoded by G1 and G2. So first we'll need some lemmas to prove this and some tools. First, if you have matrices, wait, maybe one thing important first. Here, G1, G2 encode polarizations, principal polarizations, and they have a very specific form. So that's what we want to reach in the end. But to do so, we will work with other matrices in a purely arithmetic world that do not correspond to polarizations. So here, for instance, I will write H1 and H2 that are my matrices, but those do not represent principal polarizations. So if we have like such matrices H1, H2, and U, we say that U connects H1 and H2 if we have this relation. And yeah, you can see it as a map between H1 and H2, but it's not a map that encodes a polarization again. And another lemma is that we can inverse matrices, connecting matrices. If you have U connecting H1 and H2, that is invertible in if you tensor it with the quaternion algebra. Then you can take norm of U times U inverse as the inverse matrix, connecting matrix. And this norm of U inverse will have coefficient in O0. Okay, so we can invert matrices, which is nice. Then we can we have another lemma that says we can compose these connecting matrices. So if you have two matrices H1, H2, H3, and H1 and H2 are connected, and H2 and H3 are connected as well, you can just compose them, and it gives you a connecting matrix between H1 and H3. And of course, the norm of the composition is just a product of the norms of U1 and U2. Okay, so now we can outline the strategy for the algorithm. So first we have two inputs, varieties like matrices in this case, actually, G1 and G2. And we noticed that if G1 and G2 have a really specific form, then the problem is like really easy. Indeed, if we have G1 and G2 such that the top left coefficient is the same, is some integer t, which is the same, and with the power of L. If, in addition, G1 and G2 are the same determinant, then we can just compute tau as shown here, and tau indeed connects G1 and G2. So in this really specific subcase, we have a solution just like this. But of course, G1 and G2 are not of this form a priori, so we cannot apply this as is. So the high-level approach would be to take our inputs G1 and G2, transform them with isogenies U1 and U2, such that we can apply this lemma. So in some sense, it comes like we can sum up this by just like splitting our matrix gamma as three connecting matrices, U1, tau, and U2. To do so, because the degrees of the composition, the degree of the composition is just the product of the degree, we need the degree of U1 and U2 to be a power of a prime. So that's L to the E1. And we need the top left entry of these H1 and H2 to be a power of a prime as well. Because of the lemma above, it will ensure that the composition gamma as norm, power of the prime as well. And so basically what we have to do just to solve KLPT is just to find such U1 and U2. So how do we do this? We start with some matrix, input matrix G, and we want to compute U such that this new matrix H has L to the E2 as a top left entry. And the norm of U must be a power of L, with E1 and E2 independent from G, I think. Otherwise, the algorithms like the lemma cannot be applied. Okay, to do this, we just compute U star GU, and we observe that the top left entry, which is what we interested in, only depends on A and C. And that's very important because it means that the matrix U is split in two columns, independent columns, I would say. So first, because we have two tasks, we can use the first column, A and C, to satisfy the first requirement, and then find B and D to satisfy the second one. So strategy becomes we write H being like U star GU is just some matrix. We find A and C such that this S prime is equal to L to the E2. And then we find B and D. Given A and C, we find B and D such that the whole matrix has norm a power of a prime. And so basically these two steps, the first one is just solving a Diophantine equation, which is quite similar to what we do in KLPT1. And the second step is way more subtle, I would say, but involves KLPT1 as well. And we will start with the second step. Okay, so here we assume we have some matrix U which is ABCD, but A and C are fixed, and we will assume they are coprime. And what we want is find the second column, B and D. So it's two quaternions. And we want to find them such that the norm of the whole thing, this equals, okay, I forgot something here, but the norm is like this formula, and it should be a power of L. And what we do in the algorithm is reducing this problem to a pathfinding problem in dimension 1. So we view O2 squared, which is like space the pair B and D lives, as a right module of rank 2. Then we compute some Isogeny coefficient between A and C, which is possible because they are coprime. And we fix two submodules, M1 and M2, that happen to be complementary. So we have M1 that is generated by A and C in some sense, and M2 is some other module we compute. I won't like show the details. I think the analysis is like way easier understood like when you read the paper. But what is important here is that the two submodules being like in a direct sum means that you will manage to fix the norm of U at the whole just by modifying B and D. Like you don't really care about A and C. Even if A and C are fixed, we'll be able to find B and D such that the norm is what you want, basically. So the main theorem of this section is that the second submodule M2, in which you will find the pair B and D, is actually isomorphic to an ideal in O0. So M2 and I are both like submodules of O0, and they are like isomorphic through like an explicit isomorphism. I don't write here, I think. We have some isomorphism F. The exact formula is not really important here, which is an NC homothéty. Here, maybe I forgot to say it, but N in bold font is just the norm of a quaternion in the quaternion algebra. And so being an homothéty just means that if you take an element of M2, you apply F to it, then the norm in I, like in O0, will be just multiplied by NC. Okay, so from this, what do? We just use KLPT to find some element omega in I, which are really specific norm, which is norm of C times a power of L. And because F is an isomorphism, we can apply F inverse to omega and compute the pair B and D at the inverse of omega. And so because it's an N norm of C homothéty, the norm of the result will be the norm of omega divided by norm of C, which is exactly what we want. And so we have some resulting matrix here, which have like norm the square of that. So it's a big O of p to the 6. Okay, this matrix is a bit ugly, but actually we can simplify it in some sense by splitting this into a product of two matrices, and noting that the second matrix is just of determinant 1, so it's not important, like the degree, the norm doesn't change if we remove it. So actually we can just use the first matrix for U. And note that here X and Y are quaternions you find through KLPT. Okay, so here we've done like one of the two steps, which was computing the second column of the matrix given the first one to ensure the whole matrix has a norm, a power of L. And what we need is just to compute the first column. Yes. So what we want is find A and C, such that the top left entry of the resulting matrix, which is like this formula, is a power of L. And this problem is really just KLPT basically. So we do pretty much the same in KLPT. And how we do this is just by taking O0 being like P extremal special suborder, like not maximal order, which means that it contains it contains the order Z plus Zi plus Zj plus Zk, which allows us to run like Kornacki algorithms and just solve like simpler different equations. Again, I don't write the formulas here because it's not completely trivial here for sure, and it would be like really ugly to just shoot here. If we do this as is, we would obtain a column A and C, but the output would be a bit too big, and I'm not sure even like the heuristics work in this case. So what we want to do first is have some preprocessing step on G, such that the entries of the matrix are like bound. And from this, we can ensure that the output S prime has norm big O, the size of the top left entry is p to the 6.5. And the norm of A and C are co-prime, which is required for the previous step. Okay, now if we look at what we did, we managed to compute matrices UI connecting to other matrices, such that UI is in O0. It's there is a mistake here. It's not in O0, of course. It's in M2 of O0, this is matrix. So norm of UI is a power of a prime, and the image, in some sense, of it connects G and some other matrix H that has like top left entry a power of a prime as well. And so we can finally apply our lemma. And here, computing gamma of the composition of these three matrices, we obtain an isogeny like a matrix encoding a real isogeny between polarized variety, which norm is just the product of the norms. So in this case, it's L to the E1, which is L to the 6 times L to the 6 times L to the 13. And so the total output is of length P to the 25. Okay, so that was KLPT algorithm. Now, very quickly, we can talk about what allows, what we can do with this algorithm, what it permits. So first, the question is, we have the algorithm in the arithmetic world, but it doesn't mean we can just translate trivially from superspecial abelian varieties to matrices. And so in the case of the translation of variety to matrix, I said earlier that it was solved not so long ago by Gaudry, Soumier, Spanlower, and Veselowski. But as far as I know, for generic Jacobian, we don't know how to translate between the two. That's for like variety to matrix. And then we would like to translate isogenies to matrix and vice versa. So for 2-2 isogenies, we did it in the paper. It's like a very efficient method. We just like take all the possible 2-2 isogenies. We have like 35 of them. We just actually enumerate the kernels, possible kernels, and we associate one matrix to each kernel like corresponding to another isogeny. So it's really efficient. It could be, I guess, generalized to 3, 3, 5, 5 isogenies. I don't know. So the number of kernels, different kernels, grows quite fast, I think. But yeah, I don't know up to what bound it would be feasible. And then for the translation between matrix and isogeny, we have some algorithm already that can be found in the PhD thesis of Hao Wei Chu. And yeah, it's not the problem for our smooth degrees. Okay, now if we talk about the applications of this KLPT² algorithm, first we can, in theory, just like KLPT allowed us to, in some sense, break the CGL hash functions if it used maximal orders directly. Here we can break a 2D version of CGL, assuming the inputs and outputs are matrices in math A0. Beside this, we can as well, like here we have some results above about translation between isogeny and matrices, and we can, with the algorithm, relax them. So I think, for instance, we can relax the post-smooth degree translation between matrix to isogeny to just a smooth degree one. And maybe a last, it would be a joke in the end, to be honest, but another application we could imagine would be like an analog of ski sign, but in 2D, but not the same flavor than what we have already, to be a brand new thing, probably completely inefficient. But yeah, I guess we never have enough ski signs. Finally, to conclude, I told at the very beginning that there were like no typo in the title. And indeed, the last little like discovery of this talk is that if you take the initials of the authors of this paper, well, we have to cheat a bit. For Thomas and Bowser, we have to take the first name and not the last name. But yeah, it reads KLPT². So yeah, I would like to thank very, very quickly Chris for this nice little discovery. Yeah, thank you for your attention.
Thank you very much for a great talk, Abel. As always, if anyone has any questions, you can unmute yourself and ask them, or just type them in the chat and we'll read them out loud. I really enjoyed your talk, Abel. Maybe I can start by asking of course, like the big step here was just getting a result in dimension 2, of course, but I bet that, of course, we want to reduce this p to the 25. I'm
Yes.
assuming. So
Yeah.
did you have any like idea or any hope for like what how
So
to do that?
yeah. So when we look at KLPT, the original KLPT, the optimal path would be of length big O of p, and what we have at the moment is like big O of p to the cube. If one of the two curves is zero, basically, and if for any two curves, it's I think 9 O's. That's what what was used in ski sign. Here, like the output is like way worse, of course, but it's not even clear what the so it's like p to the
Optimal is.
25, but the diameter of the graph, I think I'm not sure. It's like wait, where is it? I'm not sure it was it was like certain. So this isogeny graph is not a Ramanujan graph. It's still expansor, but we don't really know what the optimal would be. But clearly, p to 25 is not optimal. Well, it would be like really surprising. And so to yeah have a better bound here, we could either like tweak the strategy we have already and gain some values here and there, or we could try to change completely. Like it's still quite ad hoc. For instance, here the lemma is just if we have some really specific inputs, we can solve the problem. But maybe with like other specific inputs, we would have like another approach feasible. It's still like in the end, it's just like solving equations. So this is one approach. But yeah, I wouldn't be surprised. I would be actually be very surprised if there were like no way to do better than this. And probably not marginally better, but really better, I guess.
Thanks. Maybe to ask one more question. So these G1 and G2, well, basically, because like how the algorithm is set up now, you don't require anything on the input, right? As you said, the original KLPT algorithm kind of assumes that one of the inputs are special in some way, but here you guys really don't require anything special.
well, we do in the end, because for this part, where is it? Here. So to compute the first column of the matrix U, we have to solve some Diophantine equation. And here we do this by, so solving this equation is basically we take A and C to be in subspace, so that the trace vanishes. And then we can write norm of A and norm of C are just like sum of two squares, and that we solve by Kornakian. And we can write them as sum of two squares because O0 here is an extremal order and contains this. So
sorry, can I interject here? So that's not
yeah.
So that's not quite true. So this depends on how you define polarizations on so this is not really an input issue. Really, the two surfaces that you work with and that you want to find the connecting path between them, they can be really arbitrary. It doesn't go through any special surface. This thing is only needed to get like an easy parametrization of abelian surfaces. So this is Ibukiyama Katsura Ortsing parametrizes abelian surfaces with these like fixes one particular polarization of some square of a square of some supersingular elliptic curve. And then every other polarization is this ratio between the two polarizations. And I mean, the only choice that we make is we choose this fixed polarization to be the square of the simplest supersingular elliptic curve you can find, but that's not really. I mean, you can do that for anything. It just makes things a little bit easier. But in terms of the surfaces, that's just the most convenient way of parametrizing them. But that's not about the surfaces. So really, the two surfaces.
Yeah. Okay.
Can be really anything. You
maybe
could
I was not
parameterize
clear.
everything with you could choose your starting surface to be something more complicated, but there is really no. I mean, and I'm pretty sure there is probably a reduction between those two things. So it will not make the thing harder or easier. It's just more convenient to work with. But it's not really. It's more like a choice of like how you view surfaces.
Yeah, so I wasn't clear. Like, I answered the question for the algorithm itself, which used the fact that we're working with A0. But yeah, indeed, here we choose A0 and some product polarization, not that zero. But in the end, it's just like any Jacobian. It works the same way. But I think the algorithm itself, at the moment at least, still uses the fact we have A0, which is like special form.
Yeah, so I guess what I was wondering then if so thanks for the clarification first of all, but so basically you can solve the problem for any two surfaces, but your solution, so that my problem was actually like your solution always goes through G1 and G2 of a special form, like from one of the lemmas, right? You want this D in the upper corner, this one, yeah.
Yes.
So basically what I was wondering is like these special matrices, they correspond to some kind of polarization, and I was just wondering if it had any meaning, like
I mean, H1 and H2.
yeah, G1, no, G1, yes, H1 and H2.
Yeah. So what is
If
important
they are
here
like,
that
sorry.
yeah, so H1 and H2 do not encode principal polarizations. And in general, like any matrix we have beside G1 and G2 are just like random matrices. But here, considering what we do,
Not the principal one. Sorry,
yeah,
I misspoke.
they still encode polarizations. Yes.
Yes. So basically, they
yes.
correspond to some kind of surface.
Yeah. So,
My bad.
I don't know what happened if we try like the translation between varieties to these. Like in the end, we can generalize maybe if we have this. Here the determinant is 1 I think for we can generalize this to have something else, and that would encode non-principal valorizations indeed. So does it mean anything in the way we solve things? I don't think so. In the end, we just ask here, we just ask that the composition so gamma has a very special form, but anything that happens in between, it's not really important. Well, it's probably like not a coincidence if it still has some structure, of course, but in theory, it wouldn't be important. So if you somehow manage to find a different way to compute gamma going through H1 and H2 that are like completely non-polarizations, yeah, maybe it's like more generic. So maybe it will have, I don't know.
Yeah. Well, I was just, yeah, it's not at all clear to me either if like these H1 and H2, if they are like super generic elements or if they're very special surfaces.
Well, they're
So
already special, but they could be more generic than this. Like we don't, you know.
Yeah, well, thanks.
By the way, I think we have like an answer to one question I asked. So at the very end, I'm saying that there is no variety to matrix algorithm for Jacobians, but yeah, apparently Damien Aurel has something like this. If it's yes.
Yeah, like Peter says, it reduced to a problem that Aurel knows how to solve from a preprint from like almost 10 years ago that he never published, but
Nice.
we have a version of it just in case.
Okay. So yeah, I will change my slides to Aurel's no.
Is this preprint available anywhere?
You can ask an email to Aurel and he will send it to you, but yes,
So sorry, I'm asking so many questions, Abel, but I really enjoyed it. It's super interesting. So the usual KLPT algorithm again really benefits from starting with a special curve. Did you like try to see if you could do way better if you assumed that one of the curves were E0 square with the product polarization or something, or like...
Not really. The point, I think, so the question is, if you start, instead of having, for instance, A1 lambda 1, you start with a product of two elliptic curves.
Yeah, basically something, the easiest instance you can think of.
Well, in the end, we end up with a matrix, and we solve the problem for the matrix. The form of the input matrix G in that case would be what? It's not really clear.
Sorry, maybe I can answer it. So we did consider it. So that was the original version of the algorithm, and then we realized it and we tried to generalize it to like a more generic thing, and we basically get exactly the same output lengths. So you get, it's a slightly different thing. Instead of these like two matrices, you get some quite easy Diophantine equation that you get to solve, but the result is exactly the same to connecting to E0 square as opposed to connecting to between two surfaces. So that's why we think that somehow it probably doesn't go through E0 square, because otherwise it would be twice the length, I guess.
Yeah.
So for E0 square, the matrix is really just the identity matrix. So that's G. The G matrix is really the identity matrix. But if you try doing all of this that you have here, you get exactly the same output lengths.
Interesting.
For both cases.
Oh, thanks.
I also have a question. So it seems like a lot of the theoretical jump is going from dimension 1 to dimension 2 in the sense that you have to add all these polarization issues. But then once you get dimension 2, you can hope to like generalize to any dimension, where like the matrices now are like G times G matrices, maybe. And then you can like apply your algorithm like recursively, let's say like the same strategy, but do it recursively down the matrix. Did you consider that, or does it seem like there are reasons why you can't just simply generalize it? Or was it, yeah, did you consider doing it for general dimension?
Some steps are like easier than others. The Ibukiyama Katsura Ort correspondence like works in higher dimension as well, so that's not really a problem here. Defining an isogeny graph in higher dimensions, I like a generic one. I don't know if it's that easy in the end, because in dimension 2 we still have only Jacobians and product of elliptic curves, and yeah, we have this superspecial and super singular like distinction. But if we go higher, we can have like other kinds of varieties. And I think superspeciality like splits again into like 2 different subcases. Again, there is like a very nice paper by Castric, De Cru, and Smith that talks about all of this. So defining the isogeny graph, if we want like the whole thing, I don't know if it's so simple. If we don't restrict to product of elliptic curves, which is what we do at the moment, I think, when we work in dimension 4, 8. And then applying the algorithm. Yeah, it's not completely clear to me. In the end, if we're just like solving, yeah, if the correspondence works the same, I guess solving like with bigger matrices, it should be doable. But the thing is, like it's never clear to me like what steps can fail randomly at some point. So I wouldn't be surprised if there is some caveats and some obstructions at some point.
If I may, that's a topic I've thought a bit about. And one source of difficulty of doing the recursion step is that one way to reframe the KLPT² algorithm is to use like modules on Hermitian modules, and the key step they use is like find a submodule. Like so, in dimension 2, you have a rank 2 Hermitian module, and the key step is to find a submodule that is an orthogonal sum of polarized Hermitian modules of rank 1, and then they reduce to KLPT. And what makes things really nice is that Hermitian modules of rank 1, the polarization is n times the principal polarization. Now, if you start in dimension G, and you can try to look at decomposition, like a submodule which decomposes in orthogonal sum of rank 2, 3, or whatever, but then the polarizations will not necessarily be an integer multiple of a principal polarization. It can be given by some symmetric endomorphisms, but symmetric endomorphisms are much more general than just integer multiples. And I will assume that would be the key difficulty for recursive algorithm would be to solve this case of a more general than an integer, like a general endomorphism, symmetric endomorphism, totally positive symmetric endomorphism to get a fully recursive algorithm.
Okay, interesting. Thank you.
Okay. I think it seems like there's no more questions, or is there anyone else with any last questions? Otherwise, we can probably thank Abel again for a great talk. And yeah, in 2 weeks we have, should probably check this before, but
Loran.
Loran Marco, yes. She's presenting in 2 weeks, so be sure to tune in for that. And yeah, see you all then.
Thanks all.
Did you stop the recording, Maria?
Thanks for the talk.
Thanks for the talk. Bye.